This is a flip video about thermochemistry. Thermochemistry is an area of science concerned with the amount of heat absorbed or released in a chemical or physical changes. So chemical and physical changes are things we talked about pretty much all year. And in these processes, right, there's this heat, and sometimes it's absorbed, sometimes it's released. That's what we're going to be talking about. And so thermochemistry focuses on thermal energy. And there are many types of energy. Here are just some to name a few. Mechanical, kinetic, there's our thermal energy, potential, nuclear, many of these you know. Sound, chemical, electromagnetic, it keeps going on and on. There are more, but again, we're going to be focusing on thermal chemistry. So thermal chemistry sounds like the word thermos, thermals, all things that are good at containing heat. So this is all about heat for our sake. So when you hear me say thermal or heat, we can kind of use them somewhat interchangeably. So the thing about heat that you should know is that heat flows. It gets transferred. And the transfer is actually in one direction and one direction only, and that is from objects with a higher temperature to an object with a lower temperature. So in this instance right here, we have our hot chocolate, yummy, and my cold hand. And so I go to touch the hot chocolate and hold my mug like that, and I ask myself, well, according to our science laws, how does heat get transferred, right? And is that the hot is gonna make my cold hand feel warmer, or is the coldness gonna get transferred into the hot mug? So does the mug make my hand hot, or does my hand make the mug cold? Well, one of those is right and one of those is wrong. And as we just learned, since the mug is hotter, higher temperature, heat is going to travel from hot to cold. So what's going to happen then in this scenario? The mug is going to make my hand warmer. The heat is going to go from that hot cocoa mug into my hand. So there really is nothing blah, blah, blah. There really is. Cold is just a way to describe something that does not have heat, right? But rather than have to constantly say, this has heat and this does not have heat, they made up a word for it, and that's cold. And so cold is really a lack of heat. Okay, finally got that right. Now, two more words that I'm going to introduce to you that are extremely important are the words system and surroundings. Okay, so let's bring back my yummy mug of hot chocolate and my hand. Okay, and so you usually want to identify the system. And so in this case, or for our case, kind of in chemistry, our systems tend to be the things or the places where our reactions or our changes are happening in. And so for this scenario, that's going to be the mug where we're focusing on. So our mug is our system. And so therefore, anything that is not the mug, right, happening inside the mug there, the hot cocoa, everything else then is considered to be a surrounding, right? So the table the mug is on, right? The floor the mug is on, the air surrounding it, the atmosphere here, and even my hand. So my hand is my surroundings, okay? So we'll put the hand there so you know. And so another way of saying this is, if the flow of heat, right, the heat flow is from the system into the surroundings, right, then that means heat is exiting the system and going into the surroundings, exiting the system. And so we have this word for that, and this word is called exothermic. Okay, exothermic is heat exits the system. Well, if heat is exiting the system, then what's happening to the surroundings? Well, obviously, the heat's leaving the system, going to the surroundings, so the surroundings temperature is obviously going to go up. So another way of defining exothermic is just asking what happens to the surroundings. And so if you were to say the surroundings temperature went up, that's exothermic. Now, there's another type of word that's opposite of exothermic, and that's endothermic. And in endothermic, heat does the opposite, and that is heat enters a system from the surroundings. And so what would be a situation that is endothermic? And that would be something like an instant cold pack, right? Have you ever gotten injured, right? Or if you're Miss B and every time you lift, you need to ice your knees because they swell up, you're gonna use this cold pack. And just a quick chemistry behind a cold pack is that there's some inside chemicals and they react with each other. You've got this ammonium nitrate, which is a salt, and an inner bag of water, and when the bag and the salt come into contact with each other, you get the cold pack, right? And so the question is then, what is the system? And so everything inside this cold pack is the system. That water, the salt, that's the system. And what's the surroundings? Well, the atmosphere, right? So all of the air surrounding it. Okay, so now I ask myself, what's happening in this situation? Okay, and that is, let's bring our arrow back, right? And the arrow is now going to go this way, and that is any sort of heat from the surrounding goes into the system, so therefore the outside feels cold, and the heat goes into the reaction, allowing it to occur. So the reaction then needs that heat, right? And bonds are broken, new bonds are made, and the salt reacts with the water, gets dissolved. And so that needs heat to happen. And so it pulls that heat from the surroundings. Now don't forget, our atmosphere is made up of a lot of heat, right? So that air and all of that heat that's in that air goes from the atmosphere into the cold pack for the reaction to occur. And so the surrounding part of the cold pack is extremely cold. Hence the outside touch of the cold pack is very, very cold. Okay. And then one more time, let's look at another exothermic. Here is Ms. B's awesome drawing of a candle. I don't know what happened to it. I guess it's sitting in a bowl. I got artsy. And so we're going to say the candle and the bowl are the system, and the table it's sitting on, or whatever you want to say it's sitting on, and the air around it is the surroundings. And as the candle burns, it releases the heat into the surroundings, you know. And if you're ever sitting by a candle, it kind of gets a bit toasty, right? So the surroundings temperature increases. So again, just a reminder, try to think sometimes in terms of what's happening to the temperature of the surroundings, right? Try to think in terms of what is happening to the temperature of the surroundings, right? And so for that endothermic, just to revisit it, right, that is the temperature of the surroundings goes down, and for the exothermic, the temperature of the surroundings, right, increase. All right, now, another important thing is looking at these reactions or these changes using a graph. So let me zoom out here, and we'll start here with this graph right here. And these graphs, by the way, are called potential energy diagrams. Sometimes I refer to them as endo and exothermic graphs, but this is kind of the more formal name. And so let's dissect this graph or this diagram and look at the two axes. So we're going to be looking at reactions or changes that are happening, and these changes have a reactant and a product that gets made. So on this side, I'm looking at potential energy. And if you remember potential energy from a previous science class that you've taken, potential energy is stored energy, right? It's that ball on top of the hill. Remember this picture at the beginning of this video. That ball has a lot of potential, right, to actually do some work. And so that ball has a bunch of stored energy thanks to the height, right, at which that ball is at. Once the ball starts moving, then that gets changed into a kinetic energy. But right now we're talking about the potential. So I bring back this graph here, and so on this axis right here, my y is potential, my x is my reaction as time goes by, right? The progress. And so in this situation right here, my reactants have a very high potential energy, and just for the sake of, making this a little easier, let's just pretend these are the scale at which potential energy is at. So I have 0 potential energy if I started here, but this reaction doesn't even start with 100 or 200 or 300. The reactants start with 400, right? And the unit for energy is kilojoules. And so there's a lot of potential for this reaction to occur. So a lot of energy at the beginning before. So there we've got our reactants just sitting there. As the reactants go through the reaction, so we can see here the reaction happening, that energy goes up and up and up and up and up, right? All the way to a high peak of whatever, 600-700 kilojoules of energy. And then as it proceeds, right, so the reaction's proceeding into the products, right, the energy starts to decrease and decrease and decrease and decrease, right, down that thing. So what does this mean right here? What this means is in order for the energy to decrease, it had to go somewhere. Where does it go? It gets released into the surroundings, right? That energy is released into the surroundings. And then eventually you get your final products down here, right? And so in this situation, when your energy is released into your surroundings, remember that's exothermic, right? So my surrounding temperature goes up. My surrounding temperature goes up. So for example, if I start off with like hydrogen and oxygen gas and I collide them together, right? And they react to form water. So my reactants start off with a lot of energy to begin with, and they're able to release that energy into the atmosphere, into the surroundings. And when they're done being products, then their products have lower energy at the end. What does this blue line represent? Well, in order for the reaction to occur, there has to be some sort of activation energy, and that's the energy needed to activate, or in other words, start the reaction. So there's always an amount of energy needed to start any reaction, but the question is, do you have more that's needed to start it, or do you have, so here's my starting, or do you have more, right, to reach the product that's released? And so in the end, when the difference is calculated, more energy is released than absorbed. So that's an exothermic reaction. Now on the flip side, obviously then an endothermic graph is going to look like this, right? Again, these are still potential energy diagrams, but this is an endothermic one. Axes are the same, okay? I start off with my reactants, and in an endothermic reaction, my reactants have very little potential energy. Well, they need to get energy. So where are they going to get that energy from? They need to absorb it from their surroundings. So they absorb enough right here. Look, there's their maximum absorbed. And then they're releasing to make the products. But look how little they release. They absorb a ton more than they release. So therefore, right, they have more energy that they absorb. This is the difference, right? The difference. Left over is what happens here. So there's more absorbed than was released. And again, sometimes it helps to look at this compared to this. Where does that absorbed energy goes? It goes into the bonds, right? It gets used to make and break the bonds of these reactions. And so in the end, this one needed a lot more to start the reaction, a lot more energy, right, than it released. So you always have an amount that you absorb of energy, an amount you release, but the question is, which one do you have more of? So if you use more energy to start, right, it means you're absorbing more energy than you release, you're endothermic. Versus if you release more energy than you needed to start, then you're exothermic, okay? These are important graphs to know.